All right, let's dive right in and get to the very heart of anti-epileptic drugs. In this masterclass, our goal is to really pull back the curtain and understand exactly how these medications work on a molecular level to calm those electrical storms in the brain that we call seizures. So here's the game plan. First up, we're going to define epilepsy and get a handle on the different kinds of seizures. Then we'll explore the brain's super delicate electrical balance. And you'll see why that balance is so important, because understanding it leads us straight to the three main strategies that these drugs use to get things back in check. We'll wrap things up by taking a closer look at some of the most important medications, including some really interesting new players on the scene.
Okay, so before we can even think about fixing the problem, we've got to understand it, right? What in the world is actually happening in the brain during a seizure? It's time to define the chaos.
So when you boil it all down, epilepsy is a neurological disorder, and its defining feature is seizures that are both recurrent and totally unpredictable. A seizure itself is that sudden, out-of-control electrical surge firing through the brain. And this isn't some rare thing. We're talking over 45,000 people in Ireland alone. So you can see why getting this right is just absolutely crucial.
And wow, this image just says it all, doesn't it? Look at the top. You see that nice, calm, rhythmic pattern of a healthy brain doing its thing. Now compare that to what's happening below. You see the EEG from a focal seizure, with that localized explosion of chaotic firing. And at the bottom, the generalized seizure. That storm has taken over the entire brain. It's a really powerful visual of what we're up against.
Okay, so a really important thing to get is that seizure isn't just one thing. They're all different, and figuring out which kind is the first big step to treating it properly. The International League Against Epilepsy gives us this really solid framework. Seizures are sorted based on where they start. Focal, kicking off in one specific spot. Generalized, hitting both sides of the brain at the same time. And unknown onset, for when the starting point just isn't clear.
So let's zoom in on focal seizures. With these, it's all about location, location, location. Because they start in one specific part of the brain, the symptoms are a direct result of what that part of the brain does. So, a seizure in the temporal lobe, that might make someone smell something that isn't there. If it's in the frontal lobe, you might see a loss of motor control. It's like the brain's geography is literally drawing you a map of the symptoms.
Now, on the flip side, you've got generalized seizures, and these involve both sides of the brain right from the get-go. The classic example is a tonic-clonic seizure. You get the tonic phase first. That's when the body gets rigid and stiff. And that's followed by the clonic phase, which is that rhythmic jerking of the limbs that you might be more familiar with.
So that begs the question, right? What's the root cause of this electrical storm? Well, it all boils down to this incredibly delicate balancing act that's happening inside our heads all the time.
This slide just lays it out perfectly. Think of the brain as being in a constant tug-of-war. You've got your excitatory signals, with glutamate as the main player, basically shouting, "Go, fire!" Then on the other side, you have the inhibitory team, led by GABA, saying, "Whoa, hold on, stop." In a healthy brain, it's a perfect tie, a perfect balance.
A seizure is what happens when that balance gets thrown off, when the scales tip way over into what we call hyperexcitability. And this can happen for two main reasons. You could have an excitatory overload, too much of that go signal from glutamate, or faulty ion channels letting things run wild. Or you can have an inhibitory failure, where the GABA system, the brain's braking system, just isn't working.
Okay, so if one of the problems is way too much go signal, the first strategy makes a ton of sense, right? Let's just find a way to turn it down. And the way we do that is by going right to the source, the voltage-gated sodium channels. These things are absolutely essential for a neuron to fire in the first place.
Now, this is the really clever part. These drugs don't just act like a cork in a bottle. Instead, they find the sodium channels when they're in their inactivated state, kind of like they're catching their breath, and they lock them there. They stabilize them so they can't reset and fire again. And what's so brilliant about this is what we call a use-dependent block. The more a neuron is firing wildly, the more of its channels get stuck in that inactivated state, which means the drug works better on the very cells that are causing the problem. It's incredibly targeted.
This table gives us a fantastic snapshot. You've got the classics, carbamazepine and phenytoin, doing exactly what we just described. Then there's lamotrigine, which does that and adds a bonus effect of reducing glutamate. Lycosamide has this really neat, unique twist. It works on the slow inactivation of the channels. And then check out cinomabate, one of the newer guys on the block, hitting the problem from two sides, blocking sodium channels and boosting GABA. Now look at the side effects. Nausea, dizziness, pretty common. But what you absolutely have to watch out for is the risk of Stevens-Johnson syndrome, or SJS. It's rare, but it's a life-threatening skin reaction, and it's a huge deal for several of these drugs.
All right, strategy number 2. If turning down the go signal is one approach, what about turning up the stop signal? That's exactly what this strategy is all about. We're going to focus on beefing up the brain's natural braking system, which, as we know, is GABA.
And this slide just lays out beautifully that there are actually 3 different ways we can do this. First up, you have drugs like benzodiazepines. They're called positive allosteric modulators. Now, that sounds complicated, but just think of it this way. They don't have their own key to the lock, but when the natural key, GABA, comes along, they make that lock work way, way better, so the chloride channel opens more often. Okay, method 2. Stop GABA from being destroyed. Vigabatrin does this by taking out the enzyme GABA transaminase that's responsible for breaking GABA down. Less breakdown means more GABA hanging around. Simple as that. And third, we can stop GABA from getting recycled. Tiagabine blocks this transporter, GAT1, basically trapping GABA in the synapse so it can keep doing its job for longer.
Okay, on to our third big strategy. This time, we're targeting calcium channels. And this one is super important for a very specific kind of seizure, one that has a distinct rhythmic firing pattern. Now, this is where it gets really interesting, because specificity is everything here. We're not just targeting calcium channels in general. For absence seizures, the problem is this rhythmic firing that starts in the thalamus. So drugs like ethosuximide and valproate go right after the T-type calcium channels that are driving that rhythm. But for focal seizures, we need a different plan. Here, drugs like gabapentin and pregabalin bind to a specific part of the P/Q-type channels, the alpha-2 delta-1 subunit. Now, this doesn't block the channel directly. Instead, it messes with its ability to get to the cell surface. So you end up with fewer channels, which means less neurotransmitter gets released. 2 different problems, 2 very specific solutions.
All right, so we've got our 3 core strategies down. Now let's zoom in a little closer on a few other really important drugs and some of the newer, more novel approaches that researchers have come up with.
These guys represent a totally different angle of attack. Levetiracetam and its cousin brivaracetam don't even bother with the ion channels. Instead, they go after a protein called SV2A, which sits on the little bubbles, the synaptic vesicles, that hold the neurotransmitters. By latching on there, they disrupt the whole release process before the signal can even get out the door. And it's pretty amazing that brivaracetam is 10 times better at grabbing onto that target. Then you have parampanel, which works even later in the process. It waits for glutamate to be released and then blocks one of its main docking stations, the AMPA receptor. It's like putting earmuffs on the receiving neurons so it can't hear the go signals loudly.
Now, if you're looking for a drug that's a true masterclass in attacking epilepsy, it has to be valproate. The reason it's called a broad-spectrum drug is because it's not a one-trick pony. It hits the problem from 3 different angles we've just talked about. 1, it blocks sodium channels. 2, it blocks T-type calcium channels, which is why it's great for absence seizures. And 3, it boosts GABA by taking out the GABA transaminase enzyme, a true 3-pronged attack.
But, and this is a huge but, all that power comes with a very, very serious warning. Valproate is a known teratogen. That means it can cause serious birth defects, and that's why this quote is so critical. It should be avoided as a first choice for women who could become pregnant. You always have to weigh its incredible effectiveness against that significant risk.
We touched on benzodiazepines earlier, but let's be really clear about their job. These are your emergency responders. They're the go-to for stopping a seizure that's happening right now, especially in a life-threatening situation like status epilepticus, where the seizures just don't stop. But, and here's the catch, they are not for the long haul. The sedation can be a real problem. And more importantly, the body gets used to them. Tolerance builds up in just a few months, which makes them a poor choice for everyday long-term maintenance.
And here's another drug that comes with a major trade-off. Vigabatrin is a powerful option, but it's really reserved for people with tough, resistant epilepsy where other drugs haven't worked. Why? Because it has a massive drawback. With long-term use, it can cause permanent damage to your peripheral vision. It's the definition of a high-risk, high-reward drug, and that risk of vision loss is something that has to be managed incredibly carefully. So let's end by looking at what's next, with a new drug called ganaxolone. What's so cool about this one is its incredible specificity. It only targets GABA receptors that have a very specific part, a delta subunit. This kind of precision makes it a game changer for a rare genetic condition called CDKL5 deficiency disorder. And this is more than just one new drug, you know? It really points to a whole new era of personalized medicine. We're starting to move away from these broad, one-size-fits-all drugs and towards treatments that are designed for the specific genetic reason a person has epilepsy, which leaves us with this really exciting question. As we get better and better at understanding the unique cause of each person's seizures, will we one day have a perfectly tailored key for every single lock?